Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at our homework for lesson 5.1.2, starting with the M&Ms for part-to-whole relationships. And I'm going to read through this a little bit rather than paraphrase it. The percentages, fractions, and decimals are all different ways to represent a portion of a whole or a number. Portion-whole relationships can also be described in words. You can represent a part-to-whole relationship with a linear model like this one below, the number line that we've talked about in the last couple of lessons. To solve a percentage problem described in words, you must first identify three important quantities. You want to know what the percent is, what the whole is, which I refer to as the total sometimes, and the part of the whole. So remember, you've got your part over your total is equal to your percent, which is always out of 100. Now, I want to show you how this model for proportional reasoning, equivalent ratios, aligns with this diagram, which is basically showing us the same piece of information. If I use my highlighter to highlight the percent and the 100, that would be like these two pieces of information right here, where you got your percent and your 100 right here. And then you've got your part over your total, which is this portion right here, over your whole, which is right here, the total. So your total aligns with your 100%, total aligns with 100%, and the part is the numerator where the whole is the denominator, right? Here, the percentage, I guess you could call it, or the percent out of the total 100% is aligned here. So if we just kind of flipped and rotated this a little bit, we get the same kind of alignment we have here in a percent proportion. Okay, so with that being the case, it looks like here we've got our percent is 40 and our 100% always goes on the bottom. There's always 100 there, and then the part is 220. And what we would need to figure out is what was the total. So that's where our x is going to go. So if we could find a giant one that we could multiply times 40 to give us 220, we would multiply 100 times that, and that would give us our total. So let's see what we can do here. Let's see what 220 divided by 40 is. 220 divided by 40 is equal to 5.5. That's a nice giant one because it's a terminating decimal number. So if we multiply this times 5.5, we'll multiply this times 5.5, and we will get 550. And so that would be the total number of students, which is what we see right there. Okay, so using proportional reasoning to solve for the missing quantity in the proportion is a great way to solve this problem. Now, some students might do this. Some students might look at this piece of information right there and say, all right, I'm going to take, and we know if we've partitioned this, this number line into percents, it would seem logical to break it up into 10% intervals, right? So a 10% interval would have 4 intervals for the 40% portion, and then would have 6 intervals for the 60%, the other part. So if we take 220 and we divide that into 4 equal parts, we will find out what 10% is equal to. So 4 goes into 22 5 times. Wait, hold on for a second. Yeah, goes into 22 5 times, which is 20. And then 4 goes into 25 times. So that means that each one of these guys is 55. So if you take 55 times 10, that's going to give you the total, which is 550. So you can use a few different strategies. Listen, this is a big part of CPM math and the way that I like to teach math. I want to expose you to all the different concepts and all the different strategies that you can use to solve a problem. And I want you to take the one that makes most sense to you and use that as your go-to method. I want you to see from all different sides how we can approach this problem so that you better understand the rationale and the reasoning for solving these problems. All right, let's take a look at this. A shade of orange paint is made with 5 parts of red paint and 15 parts of yellow paint. So a common mistake students make is that they want to see what percent of the paint is red. The most common mistake I see is where people do 5 over 15 is equal to X over 100. 15 does not represent the total in this situation. 15 represents the parts of yellow. So I organized a little table here to show us how we can get to this answer. So if we know that the paint has 5 parts red and 15 parts yellow, there must be a total of 20 parts in there. So if we double it, it should be 10 parts, this should be 30, this should be 40, correct? And if we double that, it would be 20 and 60, which would be 80 total parts. And then if I add these guys together with these guys, you'd have 25 parts of red with 75 parts of yellow, gives us a total of 100 total parts. And that piece of information right there is what we need for the percents. Because 25 out of 100 is 25%, right? And 75 out of 100 would be the part that is yellow, which is 75%. So that would be one way to do it. The other way to do it, oops, stop that. The other way to do it would be to use the percent proportion, where you take this quantity and this quantity. The number of red parts out of the total is equal to X out of 100, and now you look for your giant one. What do you multiply times 20 to give you 100? That would be 5. So you multiply 5 times 5, and you would get 25 as your percent. Now, what is the simplified ratio of yellow to red paint? This is something where you've probably heard about ratios in the past, where when you simplify a ratio, the order in which they're written matters as far as the ratio is concerned. So they're starting with yellow information. So that's a 15 to 5 ratio. And you could write that in fraction form, 15 to 5, and then we would want to simplify that fraction, right? So you can simplify ratios the same way that you simplify fractions. Look for a common factor. And so 3 over 1, 3 corresponds to the yellow and the 1 corresponds to the red. 3 to 1 ratio would be the ratio of yellow to red paint. Now, if you said yellow to total, it would be a 3 to 4 ratio. If it was red to total, it would be a 1 to 4 ratio. But this is yellow to red, so we're going to take the yellow quantity and the red quantity and simplify it. All right, Janelle earned 90% on a test and got 63 points. How many total points were possible on the test? This, by far, is the most complicated kind of a problem to solve if you don't use your percent proportion. Using the diagram is very, very helpful too, but a lot of times students think about shortcuts and think about changing this to 0.9 and then multiplying it times 63, which is the wrong way to solve this problem. And that's one of the reasons why we use the percent proportion and we put all the information into the proportion before solving, is because people want to go straight to shortcuts that they've learned in 5th and 6th grade, and those shortcuts don't apply to this situation, okay? So let's take a look at it with the diagram, since that's what the directions told us to do. If we know that 90% is 63, then I'm going to create a number line that goes all the way to 100%, and I will break it up into 10% intervals. So then we can take the first 9 intervals, which is 90%, and assign the 63 points to that 90%. So if you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, if you've got 63 points that we break up into 9 equal parts, each one of those parts is going to be equal to 7. Which means when you extend that out to the total, it's got to be 70 points on this test. So let's go ahead and see if that actually works. If you got 90% on a test that was worth 70 points, then we change that to its decimal equivalent, which is 0.9, and multiply that times 70, and I guarantee you 0.9 times 70 is going to be equal to 63, and it is. So we know that's the correct answer. Now, let's look in terms of the percent proportion. Remember, you're looking for a part, you're looking for a total, and you're looking for a percent. So So reading through this represents the percent. That's pretty obvious because you see the percent signs. Let's go ahead and write in 90%. This quantity right here is the score that she got, but she didn't get 100%. She got 63. So the total is what we're looking for. We've got the part, which is 63 points. It's the total that we don't know. So part over total equals percent over 100. And now you can use a giant 1, which I would not recommend in this situation, although, let me just show you this legal move. 90 out of 100 can be simplified down to 9 over 10. And so if you write an equivalent fraction to this percent on the right side, now our giant 1 is easier to figure out because you take 9 times 7 is 63, so we'll take 10 times 7, which is 70. And this is essentially what we did in the diagram, is we based it on this simplified version to have a multiplier being multiplying times 7 10 times. Okay, so percent proportion diagram. Two great ways to solve problems like this. All right, let's take a look at some area diagrams. The diagram at the right is a floor plan of Randy's apartment. All measurements are in feet. Okay, good. Use the diagram to answer the following questions. What are the dimensions of his living room? So here's the living room right there. So if you look at the information that you have on the side, you know it must be 10 by 15, right? Oops, why am I doing that? I should be highlighting. 10 by 15. And so to find the area of this room, you multiply base times height, which is 150, and we express our answer as square units because we're finding area. How many squares would fill up that space? 150 square feet. Now, Randy's friends are coming to visit him. He plans to keep them out of his bedroom. All right, hold on for a second. Let me go ahead and nobody's going in the bedroom. Stay out of the bedroom. That does not count here. So find the area of each of the other 3 rooms he will have to clean. What is the total area of the rooms he will have to clean? Okay, so this is a 7 by 9, which is 63. This is 7 times 15, which is 105, plus the 150. Add those 3 together, and you get your 318 square feet. Now, do you notice something here? Notice how I have chosen, in some instances, to use the exponent of the number 2 to represent square feet. And here I use the word square feet. This is the reason why I tend to use the words in 7th grade a little bit more than the exponent. Because I see a lot of people that think that exponent 2 means the word square. And so they'll say 318 square feet. And that is absolutely the wrong way to write it. Please do not attach the exponent to the number. It is telling you the kind of unit that you're talking about for the feet. So if each one of these units is 1 foot long, right there, then this is a square foot. Okay, it's 2-dimensional. This is 1 square foot, a 2-dimensional square, right? That's what this is supposed to be telling you. And this is 1-dimensional, so this is just 1 foot here, this is just 1 foot here, this is just 1 foot there. So the square feet implies that it's a 2-dimensional sort of representation. Now, what would 3-dimensional look like? It would look something like this. That's a cube. So if this is 2 feet in this direction and 2 feet in this direction and 2 feet in that direction, it would be a total of, oh shoot, no, let's not do it that way. Sorry. I'm going to confuse the issue. I don't want to give you too much information. So let's just do this. That's a square foot, and then we'll take and make it 3-dimensional. So that's 1 cubic foot because it's forming a cube, right? A 3-dimensional object. So the exponent is a 3. We'll get more into that later. In the meantime, if you're ever confused, this is the reason why I'm bringing this up. If you're ever confused about where that exponent, the number 2, goes for square feet or square inches or square miles, then don't use it. Just use the words. That works just fine for declaring your answer. 318 square feet in words is perfectly acceptable. All right, moving on. Adding and subtracting fractions and mixed numbers. Remember, 2 things have to be considered here. The fact that you're adding a positive to a negative, which means there's going to be a subtraction happening on because there's going to be 0 pairs, and the fact that you're adding fractions together, which require common denominators. So I'm looking at these two and I'm thinking, all right, my common denominator could be a 10 because if I multiply 4 over 5 times 2 over 2, I get 8 over 10. But remember, that was a negative 4/5. So it'll be a negative 8/10 plus a positive 3/10. And now what we're going to do is we're going to add these integers together in the numerator. You've got 8 negatives and 3 positives. So do you have more negatives or more positives? You have more negatives, right? And how many more negatives are there? If you wanted to model this using integers, right? 1, 2, 3, 4, 5. Oh, that's too many. You need 8 of them. 1, 2, 3, 4, 5, 6, 7, 8, and then you got 3 positives. 1, 2, 3. Do you see these guys all form the 0 pairs? 3 negatives, 3 positives, leaving you with 5 negatives left over. So that would be negative 5 over 10, which then simplifies down to its simplest form. Here is a subtraction problem that involves mixed numbers. Now, I know what people want to do. They just want to take 2 minus 1 is 1 and 5/8 minus 1/3 and declare that answer. But you can't always do that. Sometimes you can, but you shouldn't. This is what I recommend you always do. Change these to mixed or to improper fractions. So this becomes 16/21 over 8 minus 3/4 over 3. And now get a common denominator. And it looks like we'll just use the coat of arms here because 8 times 3 will give you your common denominator of 24. And then that ends up being 63. That ends up being 32. And when you take 63 minus 32, you get 31 over 24, which is an okay answer. But if you rewrite it as a mixed number, 24 goes into 31 one time with a remainder of 7. So it's 1 and 7/24. That's a way I recommend you do it. And then you don't ever have to worry about borrowing from the whole number. But in this case, I don't think you really needed to borrow from the whole number. So let's go ahead and solve this using a more traditional method where we're going to change these so they have common denominators. And that means I'm going to multiply this times 3 over 3 and this times 8 over 8. And so that's going to become 15 over 24 minus 8 over 24. Okay, so now 15 minus 8 is 7, so it becomes 7/24, and 2 minus 1 is 1. The reason why this was so easy to do is because you could take away 8/24 from 15/24 without borrowing from the whole number. So this turned out to be the easier method. You can go either way. If you're totally okay borrowing from the whole number, go ahead and use this method. But if it's ever confusing about borrowing from the whole number, I recommend changing both of those to improper fractions and then working through the process. All right, and then the last problem where we are looking for scale factors. And so remember, scale factor, you got to take the known quantities. So we don't know the 15 and the x. We don't know the, let me do this one in green, the y and the 18. We do know that these sides here, the longest sides are 50 and 30. So that's what we're going to use for our scale factor. So you can use the formula where you take the new over the original. It says that it doesn't, see, this is the thing. It doesn't always tell us which one was the original. It sort of implies that you went from B to A. And some people look at this statement and think you went from A to B. So how do you know which one was the new and which one was the original? And I'm going to say it doesn't matter because we're just going to take this ratio of 30 over 50 and we are going to simplify it down to 3 over 5. Okay? Now, this is a fraction that's less than 1, correct? So this would be the scale factor if you were going from the larger one to the smaller one. You would multiply times 3/5 because x has to be smaller than 15. So the scale factor has to be a number less than 1 to go from 15 to the smaller side. Now, when you're going from 18 to the y, this is getting bigger. So we are going to take the reciprocal of our scale factor as if it was 50 over 30, and this would be the same as 5 over 3. So these are your two scale factors. It's either going to be the 3 over the 5 or the 5 over the 3. And you just have to decide which direction you're going in. and whether it's getting bigger or smaller. Okay, so with that being the case, if I take this problem here and I say x has got to be whatever 15 times 3/5 is, then that's going to become 45/5, which is equal to 9. And going in the other direction, we're going to take 18/1 and multiply it times 5/3 because it's going to get bigger, and that's going to become 90/3, which is equal to 30. Okay, so back to the beginning. Find your known quantities. Simplify that ratio in both directions. Okay, going either 3/5, which could be changed to the decimal number of 0.6, or changing it to 5/3, which would be a clunkier 1.6 repeated multiplier. So in that case, you'd probably just want to leave it as a fraction and do the fraction multiplication rather than this decimal multiplication. I think that's it. We have completed the homework. Hooray. All right, so let's move on to, oops, stop it. Let's move on to the next, oh, that was a long one, to the next activity. Here, bye.
Hey, feeling good, like I should.